Hello everyone. Today we discuss about Doppler effect from oscillation chapter. Let us see some application of Doppler effect. To measure the speed of an automobile, a radar, a sonar, blood flow meter, tracking satellite, stars moving towards the earth or away from the earth. In this application, we can observe that the Doppler effect is the principle used. Let us discuss Doppler effect theory in detail. The phenomena of the apparent change in the frequency of sound or source and the observer is called as Doppler effect. In Doppler effect, we can observe the following changes. Both the source and observer at rest. When the source moves towards the stationary observer, when the source moves away from the stationary observer, source is at rest and observer in motion. When the observer moves towards the stationary source, when the observer moves away from the stationary source. In the first condition, both source and observer at rest. Suppose S and O are the position of the source and the observer respectively. Let N be the frequency of the sound and V be the velocity of sound. In 1 second, N waves produced by the source travel a distance SO, that is equal to V. It is shown in the figure. So from this we can find the original wavelength of the sound wave lambda is equal to V by N, equation 1. The original frequency N is equal to V by lambda, equation 2. When the source moves towards the stationary observer, if the source moves with the velocity Vs towards the stationary observer, then after 1 second the source will reach S dash such that S dash that is equal to Vs. Now N waves emitted by the source will occupy a distance V minus Vs only as shown in figure. Therefore, the apparent wavelength of the sound lambda dash is equal to V minus Vs divided by N, equation 3. It is nothing but change in wavelength. Therefore, the apparent frequency N dash is equal to V by lambda dash. In equation 3, we know lambda dash value that we can substitute. Therefore, that is equal to V by V minus Vs into N. Equation 4. By comparing equation 2 and 4, we can conclude that N dash is greater than N. It means the pitch or frequency of the sound appears to increase. Condition 3. When the source moves away from the stationary observer, if the source moves away from the stationary observer with velocity Vs, the apparent change in frequency N dash is equal to V by lambda dash, that is equal to V divided by V minus of minus Vs into N, that is equal to V divided by V plus Vs into N. Equation 5. By comparing equation 2 and 5, we can conclude that N dash less than N. It means the pitch or frequency of the sound appears to decrease. In condition 4, source is at rest and observer in motion. S and O represent the position of source and observer respectively. The source S emits n waves per second having a wavelength lambda is equal to V by n. Consider a point A such that OA contains n waves which crosses the ear of the observer in 1 second as shown in figure. That is, when the first wave is at the point A, the nth wave will be at O, where the observer is situated. Fifth condition. When the observer moves towards the stationary source, suppose the observer is moving towards the stationary source with velocity Vo. After 1 second, the observer will reach the point O dash such that OO dash is equal to Vo. The number of waves crossing the observer will be n waves in the distance OS in addition to the number of waves in the distance OO dash, which is equal to Vo divided by lambda. It is given in the figure. Therefore, the apparent frequency of sound n dash is equal to n plus Vo divided by lambda. That is equal to n plus Vo divided by, we know the value of lambda, that is nothing but V by n. So from this we can write n dash is equal to n plus Vo divided by V into n. Here we can take n as the common. Therefore, n dash is equal to 1 plus Vo divided by V into n. So, taking LCM, we can write n dash is equal to V plus Vo divided by V into n, equation 6. Comparing equation 2 and 6, we can conclude that n dash is greater than n. It means the pitch of the sound appears to increase. When the observer moves away from the stationary source, suppose the observer is moving away from the stationary source with velocity Vo, therefore the apparent frequency of sound n dash is equal to V plus minus of Vo divided by V into n. Therefore, n dash is equal to V minus Vo divided by V into n, equation 7. By comparing equation 2 and 7, we can conclude that n dash is less than n, the pitch of the sound appears to decrease.